Shane is here to answer your questions. So there is one from Xudong.
Oh, yeah. So my question is that, so first, great work. And you mentioned that you can actually predict those requested resource and the duration. I was just wondering, like, will it also be possible to predict other Java characteristics like node affinity, priority, and even deadline? And will this also be helpful in your setting?
Yeah, that's a very good question. So there are other job properties like the customer name or the deadline, as you mentioned, different affinity constraints. Right now, I mean, it would be possible to add other stages to our model. But after you ask your question, it makes me wonder whether, you know, we should be rethinking this. Like, rather than having another layer for every other piece of information, there are ways to do like one LSTM that does everything jointly, and I think that's probably a better future direction. So it is possible, but also you're gonna have to think about your question more.
Thank you.
You're welcome.
Great. Other questions? From Rohan.
Hello. Hi. So my question is, how far into the future can you predict with reasonable accuracy? Do you see a trend where if you like go really far, the accuracy significantly drops? And is the amount of predicted future traces enough for you to deploy more resources beforehand?
Yeah, that's a good question. So I mean, for one, we're working with the Azure public trace, and that was only like a 30-day period. So we didn't really get into testing very far into the future. And then I don't know the answer for that one. And then for our own internal trace, we collected it for a longer period of time. But once we carved it up into like a training set, development set, test set, like distinct in time, we didn't revisit that question, which we did consider at some point, like rolling this forward and you know, looking at further higher horizons into the future. But even for our internal one, we did do it for up to a month in advance. So the end of the training set and the end of the test set were 1 month apart. And we were able to predict the future workload a month in advance pretty well within our confidence bounds. I know internally we prefer more notice than 1 month. So I think that's something we still need to like investigate further, because I mean, strategically, people would like to know the future workload next year or even further. So but in the medium-term capacity planning, we validated it, and for longer term, we don't know yet.
Thank you.
You're welcome.
Next questions from Vic, please.
Yeah, first, like, great work. So I'm curious about like the robustness of like this like machine learning model, because suppose that sometime maybe we collect like the training information, there are some like noise or error. So do you have like some like investigation of like the robustness of this model?
Yeah, that's a good question. So I don't think we did like a focused study of the robustness of the model. So pretty much anything I could say would be a bit of BS. So, but I think like the model was designed in a way to be able to like generalize to new time periods. So like overfitting is like a huge problem in machine learning. So we try to design it from the bottom up to not overfit, to have too much information from each period, and then be able to generalize well to future periods. But again, that specific question, like you know, how do we deal with it? And actually, there are other little features that we included to make the future generated work very sensitive to the more recent past. That's something we added later that actually worked much better than just training on the entire training set. So I think that there was some kind of weird period in training. The model does have the ability to sort of ignore that when it's generating the future. So I think that is true.
Thank you.
You're welcome.
Next question is from Stephen.
Hello, am I on? Yes, hi. Great work, Shane. Steve Han from Google. I'm curious whether or not you thought about using this approach to try to reason about the probability of very bad things happening. Because obviously one thing that you care about is kind of optimal scheduling and optimal resource usage and efficiency. But another thing people often care about is what's the likelihood that I will not be able to satisfy my customer demand? And how do I actually weigh that risk against the extra buffer maybe I'm going to have to hold on to based on this thing? And using multiple runs of your generative process perhaps to look into that. Is that something you've thought about or explored, or does it make any sense?
Yeah, it does make sense. I mean, we basically sample from our model, so we do generate tails, and we can sample a lot and kind of get to the 99th percentile of what we expect to happen. But like intuitively, and I've tried to find out how to verify this. So if anybody knows, let me know. But like the accuracy of the percentiles gets worse and worse as you move away from like the median, right? So I think that what you're saying makes a lot of sense to me, that rather than optimizing for the median or even the distribution, of be doing like a quantile type regression. Like we care about the 99th percentile events. We focus on those, and our loss is purely sensitive to those from the very beginning. So I think that we can optimize our model for those kinds of rarer events or the higher percentiles. But we didn't try that. But that's an interesting question. And I think another flip side of that is like just to also on this topic is about like anomaly detection, right? Which is also an interesting thing. Like if something does happen, can we say this is very unexpected or very unlikely according to our model? And our model does allow that because it computes an actual probability of observed data.
Thanks.
Yeah, thank you.
Next question from Ashaka.
Hi. Do you also think that using models like transformers instead of LSTMs might also help you reduce the latencies or reduce errors in prediction? I do see that you mentioned it in your related work, but do you have any intuition about what to use or why you used LSTMs?
Yeah, that's a good question. So I think like for us, this is the simplest kind of, easy to implement, very well behaved system that you could implement that would be able to model this very accurately. I think transformers are also very simple and well behaved, but they're just a little bit beyond LSTMs, and then I think that's a logical next step. But also transformers have these amazing properties that allow them to scale very well to huge amounts of data and do very parallelized training. So transformers is definitely something that you can explore to try and super parallelize all this. And then another question we also get a lot of is why not use the generative adversarial models that can help make sure that the data you generate is actually very realistic by actually plugging in a discriminator that's also trained that says like, does this look realistic or not? And again, I think that's just like the next step. And it actually within like that kind of adversarial training, you actually also need some kind of base models, and that's where the LSTMs that we propose can still function. You can just take our exact system and then wrap one of these GANs on top of it. So I think those are the two things that I get asked about the most, is like for extending this is like to transformers and to GANs. And yeah, we mentioned that a little bit in the paper, but it's still kind of future work.
Thank you.
Thank you. We have another question from Brian. Please, Brian Kim.
Hi. So thanks for the great talk, and I really appreciate how the generated workload could be useful for predicting future capacity planning and such. But you showed a qualitative comparison between the real trace and the generated trace, and it does look visually similar. It does seem like it's capturing the characteristics. But does it make sense to come up with a quantitative similarity score? And would you say that having a higher quantitative similarity score would mean that it will be useful for use cases such as capacity planning?
Yeah, that's a good question. So in general, like beyond this work, but there's lots of generative models for generating images and text and audio waves and things like that. And usually the quantitative evaluation that people use is just which model assigns the highest probability to the test set, to the unseen data. If you've got a good generative model, not only should it be able to generate data, but if it's probabilistic, it should assign a high probability to unseen data. And we do use that. So I think of that as being our kind of quantitative measure of trace quality, but there's lots of other measures you could use, like transition probability matrices and compression-based evaluation. So, but we kind of went with this one based on probability. And I think in our paper, the ones that have the highest score for most probable, so under the quantitative metric, which are the ones that score the best, do also work best in our applications. But that I don't know about that link directly. Like I would say for somebody that's using your code and trying this to do extrinsically evaluate which one works best in your applications, because you never really know, right? So we evaluate it within scheduling and within capacity planning. the different models. And I wouldn't say necessarily that, like, it was a good question that you asked that I hadn't really thought about before. It was like, how does the quantitative measures correlate with these extrinsic evaluations? And right now I'm sort of just relying on the extrinsic ones directly, but I don't know the connection. I think it's pretty linear.
Thank you.
Thank you.
So we have another question from Slack. So Vic will ask representing Jingchen, please.
Yeah. So the question is that, like, suppose that, like, we are using, like, the workload generated by this, like, machine learning model. So it means that, like, this workload is predictable. And currently, like, there are many, like, scheduling algorithms that try to use machine learning. So does it mean that it makes, like, some, like, machine learning based approach meaningless because, like, the workload itself is predictable, generated by a machine learning model?
Yeah, it's a good question. I mean, I have thought about this too, that, you know, we're using machine learning to generate the workload, and then maybe we're using machine learning to schedule the workload. You know, what is the implications of that? You know, and I don't know. I think and also whether when you're training a machine learning scheduler, can you start from this historical data and, you know, end to end, the whole thing is, say, like trainable through backpropagation or something like that, or at least through reinforcement learning, which the scheduler is trained by anyway. So do you want to turn it into like components like we do and use machine learning to have a very good workload generator and then use machine learning to have a very good scheduler? Or is there some end-to-end approach that can link all this together in some coherent way? I think that would be a great contribution. Yeah.
Great, so that ends our session. Thank you very much for our speakers, Hao, Yuhui, and Shane, for presenting your really great work. And thank you for Vic for help organizing the session. People who have more questions, please feel free to stay around and talk. Yeah, so that's the end of session 8. Thank you for.
Thank you for the great talk. We have a question from the audience. Gao from the audience, do you ask questions?
Okay, thank you. Great presentation and work. I have 2 questions. I'm going from Technological University. The first one question is, I only noticed that your resource capacity is static, and how do you address the dynamic resource capacity? The second question is, why do you utilize the LSTM? And based on my shallow understanding about generative models, there are three sub-decisions. The one is flow-based generative model, and our second is VAE, variational encoder. The third is GAN, generative adversary network. So why do you utilize the LSTM instead of another 3 commonly used generative models? Yeah, this is my 2 questions.
Yeah, thank you for your question. So, so on the first question, what do we do about changes in the amount of capacity? So this work is really about demand modeling. So in our cloud and other public clouds, at least for VM workloads, we always provision enough physical resources so that essentially what we run is what people demand. So if you ask for a VM, you can run it on the cloud. Like we were sort of over provisioned. So so we always try to make sure we have enough capacity behind the scenes so that the VMs that people do request can run. So we took just the observed trace as like the actual user demand. So the model is for demand, not for the interactions between, you know, the workload and some like a limited capacity in the system, which is something we're interested in, but it's another like layer of complication. On your second question, like why do we use sort of like the vanilla long short-term memory neural networks? Like, I think in some ways these neural networks are kind of the simplest, but also the most powerful network that can actually solve the problem very well. And they're well behaved, they're easy to train, and it's not as much kind of it's kind of a science now as opposed to an art. You know, to do like a generative adversarial network, you need like something like an LSTM inside to actually generate to be the generator and be the discriminator. So like you can actually take our neural networks and put them inside a GAN and train, you know, that way. And I think that's a natural like next step for this work as well, because it's something we didn't explore. It could potentially improve performance, but it also really increases the complexity, how long it takes to train your system and things like that.
Okay, thank you for your explanation.
Yeah, you're welcome.
Thank you. We have another question from the audience. Jun Huang.
Hi, this is Jun from OSU. I have a question about the insights that behind the reason that you think LSTM can be a tool, maybe a future tool for our system design or systemization, because why LSTM will work for example for NLP area, because it can find the sign deeper and complex relationship between the sentence, between the words, but I don't know about is there maybe some deep connection between the jobs? Maybe this LSTM can look through the job. They can predict the code, maybe predict the code structure or dependency. Can you give us some insight behind why do you think we cannot model this job prediction using mathematical model? Why should we use LSTM model? Yeah, that's all.
Yeah, it's a good question. So traditionally, people would sort of assume that the jobs arrive independently. And then like the time between jobs is like a Poisson distribution, like with a certain arrival rate. And what we found in our actual cloud workloads is that, if one job arrives of flavor A, you're very likely to see another flavor A again. And then the next one could also be flavor A, but maybe after flavor A, you tend to see flavor B. And if flavor A ran for 2 hours, then flavor B might run for 1 hour, or so there's very complex dependencies between jobs, as customers are actually running real applications that have these sort of patterns, and kind of naive approaches, like traditional approaches, can't really capture those dependencies or those even long range dependencies. So in LSTM, I think it has a lot of potential in systems because it's actually a very, it's not that hard to use, right? There's good tools like tutorials, PyTorch, TensorFlow, lots of libraries, lots of support. So if you can find a way to model a systems phenomenon, with this kind of representation, with this kind of LSTM model, you may find you can generate or predict what happens next much more accurately. And in our paper, we do call them jobs, and we evaluate on virtual machine workloads. But just talking to people since in the review process and at the conference, people see things like network traffic as being if you can visualize it in our paper, the way we show these boxes with sort of widths, that could be something you can model using an LSTM. Or people talk about caches, the hit rate. So each rather than a job, you have an object that goes into cache memory, and then how long until it's accessed again is kind of the width of the box. So I think there's lots of applications and systems that have this kind of complex correlations between different instances of something over time, and LSTMs are just a great, amazingly powerful tool that can do this with not that much work by us as a person to implement it, and you let the LSTM do all the work, use its memory and state to learn all these complex things.
Okay, thank you. I think you answered my question. Very good. Thank you.
Yeah, thanks.
Thank you.